Hello and welcome to the second part of Lesson 5. In the previous part of Lesson 5, we used force balances to obtain the velocity profile and volumetric flow rate resulting from a fluid flowing in a cylindrical tube. From these solutions, we were able to construct a relationship between viscosity, geometry, flow rate and pressure drop. And this showed us how we can use capillary flows to measure viscosity so long as we know the fluid obeys the Newtonian constitutive equation. In this part of Lesson 5, we're going to repeat the derivation, but using the Navier-Stokes equations instead. This will give you an example of how to solve the Navier-Stokes equations in cylindrical coordinates, and also give you another way to arrive at the viscosity relationship we saw in the previous part of this lesson. So, here on my blackboard, I'm going to draw a diagram first and foremost. Remember that drawing a diagram helps us to visualize the flow situation. This is the same situation that we had in the previous part of this lesson. I have a cylindrical pipe of length L and of radius big R, and across this pipe I have a pressure drop delta P. I'm going to place my coordinate axes on the center line of the pipe, and I'm going to do that because I know that that will correspond to my velocity maximum, which means it corresponds to my zero shear stress boundary condition as tau equals mu du dy, and at maximum velocity I have zero first derivative, which means I have zero shear stress. So let's work through that four-step protocol that we used to solve the Navier-Stokes equations in the last lesson. The first thing we want to do is to justify setting the substantive derivative on the left-hand side to zero. And we're going to do this by examining our flow geometry. We can see that we just have flow in a pipe. The pipe is of constant diameter. It would be pretty reasonable to assume that we've just got flow in the z direction. That flow is steady, it's unidirectional, there is neither temporal nor spatial acceleration, which means that my substantive derivative is zero. Happy days. Brilliant. So, we can set the left-hand side to zero and write out the remaining terms in vector form of the Navier-Stokes equations, and I'm going to examine the remaining terms. Now, because my pipe is horizontal and my principal velocity component is in the z direction, gravity has no bearing on the problem, and so I'm going to set my body forces due to gravity to be equal to zero as well. Now, I'm going to specify my coordinate system. We've got a cylindrical pipe. So therefore, cylindrical polar coordinates are going to be our coordinate system of choice, not Cartesians. Moreover, we can formally identify which velocity components we now have. In the way I've written my coordinate axes, I can see that my principal velocity is going to be in the z direction. In fact, that is my only velocity. If I think about how this z direction velocity changes, it's just going to change with a function of radius, because my flow is fully developed, we're far from the entrance and exit of this pipe, and wherever I look along the length of this pipe, I'm going to see the same velocity profile. Vz only changes with radius, it does not change with length. If I think about the pressure in the problem, I have got a pressure drop of delta P across this pipe of length L. So my pressure changes in the z direction, and we can quantify that change. And if we can justify the fact that my streamlines are straight and parallel, there's no streamline curvature, there's no pressure gradient transverse to that streamline curvature, then the only pressure gradient I have in this problem is in the z direction. So P equals P of z, and that's approximately delta P over L. Brilliant. So let's now simplify the Navier-Stokes equations into our chosen coordinate system. The left-hand side is zero because my substantive derivative was zero. My only pressure variation is pressure variation in z, and that is minus delta P over L. My only velocity direction is Vz, and that Vz changes in R. So if I look in the table in my notes of how the z direction Navier-Stokes equations are written in cylindrical polar coordinates, I'll be able to pick out that only the z direction velocity changes as a function of radius, and I get that second term that I've written on my blackboard. Mu 1 over r d by dr of r dvz by dr. That is the only non-zero component of the Laplacian. Right, so the final step in our protocol is to find boundary conditions. Now, because of where I've placed my axes, I know that the z direction velocity is 0 at pipe radius, little r equals big R. And that's just a no-slip boundary condition. The pipe walls are stationary, the pipe's not moving, and the fluid is stuck to the wall at the wall. So Vz equals 0 at r equals r. At the centre line of the fluid flow, I know that I'm furthest from the walls. I have got a symmetry in this problem, and so my velocity will be at a maximum, which means that there's a turning point, which means that the velocity derivative with respect to r is equal to 0. And if we remember Newton's law of viscosity, tau equals mu dvz by dr, if dvz by dr equals 0, tau equals 0, which means I've got 0 shear stress on this centre line, which is why I've placed my coordinate axes on the centre line, because it's easy to evaluate the integration constants. So that's my problem set up. Let's now integrate and solve. So there is my second order ordinary differential equation. Let's take the first integration step. I've moved the pressure terms to the left-hand side. I've also moved the viscosity term to the left-hand side. And when I do that, we can see that also pre-multiplying the derivative on the right-hand side, there's a 1 over r term. So I've moved that 1 over r term to the left-hand side and also the dr term. So the left-hand integral is written delta p over mu L multiplied by r dr. And on the right-hand side, I simply have the derivative of d of r dvz by dr. So if I integrate this, I will get delta p over 2 mu L r squared plus my integration constant on the left-hand side is equal on the right-hand side to r dvz by dr. I can solve for my integration constant by use of boundary conditions, and I know that at r equals 0 on the centre line of the flow, I have 0 shear stress. 0 shear stress implies that dvz by dr equals 0, so therefore C1 equals 0. Let's take that second integration step, and I'm going to write this integral as a definite integral now. Delta p over 2 mu L integrated with respect to dr is going to be my velocity profile between little r and big R. So if I integrate this, my velocity profile can be written as delta p over 4 mu L big R squared minus little r squared. And I didn't have to use a definite integral here. I could have evaluated this as an indefinite integral, and I would have got exactly the same result. So why don't you try doing that as part of your homework? Now, I have my velocity profile. It's parabolic, as we expect. And if you recall in the last part of this lesson, the motivation for finding the velocity profile was to take another step, which was to find the volumetric flow rate, which is a parameter that we can easily measure experimentally. And that easily measured experimental parameter can then be combined with another easily measured experimental parameter, the pressure drop, and the resulting equation rearranged to give us viscosity equaling a function of geometric terms about the pipe, radius and length, the pressure drop, and the volumetric flow rate. And so we can see that the velocity profile that we've obtained from the Navier-Stokes equations is exactly the same velocity profile that we obtained using the force balance approach. And again, just as a reminder, the volumetric flow rate would therefore be the sum of all these velocity components over each individual sort of elemental radius, elemental peripheral radius that we've got. So we write the volumetric flow rate as Q is equal to 2 pi r times Vz of r. And we integrate that with respect to dr between the centre of the tube and the tube radius. We rearrange the final result to get the viscosity equation that we had in the previous part of this lesson. So let's summarise a few key points. We've just solved the Navier-Stokes equations for pipe flow in cylindrical coordinates. We carefully judged where to put the axes because this allowed us easier treatment of the boundary conditions. And we obtained the same result as the force balance approach. So that's another way to get to the same answer.